Hello everyone. In this video, I'm going to explain how Tom uses Q-learning to find Jerry in a 5x5 grid. Before we begin, let's briefly talk about reinforcement learning. A reinforcement learning task is about training an agent which interacts with its environment. The agent transitions between different scenarios of the environment referred to as states by performing several actions. Actions in turn yield rewards which could be positive, negative, or zero. The agent's sole purpose is to maximize the total reward it collects over an episode. Let's understand this with an example. Take the Tom finding Jerry example in this case. Here, the environment is a 5x5 grid. Tom is our agent interacting with this environment. Actions are ways in which Tom can move in this environment. Four possible actions considered here are left, right, up, and down. Okay, now that we know the basics, let's define our task. The task for our agent Tom is to find the location of Jerry. So, how do we accomplish this? In simple terms, we let Tom take the actions and move around in the grid until it finds Jerry. But at the same time, we limit the number of moves that Tom can take to 10. Thus, the episode ends when either Tom finds Jerry or when Tom exhausts its limit of 10 moves. Let's define the concept of reward. Every time Tom finds Jerry, we give it a reward of plus 10 points and we update the total wins by 1. But we are also interested in finding the most optimum path, so we penalize Tom for every additional step that it takes by giving it a reward of minus 1. Let's talk about states. States can be roughly understood as possibilities for this entire game. Formally, every scenario that an agent encounters is called a state. The agent transitions between different states by performing actions. In this case, our agent Tom can be at 25 locations in the grid. In a similar manner, Jerry can be at 25 locations in the grid. This makes the total number of possible states as 625. The same is depicted on the vertical axis here. For the current grid location of Tom and Jerry, state value is calculated based on hash mapping. Its current value in this scenario is 171. If you aren't familiar with hash mapping, just understand that it maps every possible location with a unique value between 0 and 625. We have a Q table which contains the Q values for every state action pair. So, the dimension of Q table is 625 into 4 in this case. What's a Q table and what are Q values? More about that in a bit. Let's define policy. Policy, in simple words, is an agent's strategy. Imagine Tom taking random actions to find the position of Jerry. Now that would be a random policy. Similarly, you can have a greedy policy where Tom will always take the best possible action at the current instance. That would be a greedy policy. In the current example, we employ an epsilon greedy strategy. Here, initially we explore the environment more and exploit the environment after we have learned sufficient information about the environment. The exploration rate is governed by this equation. During the simulation, you would see the exploration rate decreasing from 1 to 0.01. It basically means that the agent is exploring more initially and exploiting more later on. Let's now understand Q table. What is a Q table? Q table is just a fancy name for a simple lookup table where we calculate the maximum expected future rewards for action at each state. Basically, this table will guide us to take the best action at each state. Moreover, it will also tell us how likely are we to succeed if we take a given action. In the Q table, the columns are the actions and the rows are the states. Each Q table score will be the maximum expected future reward that the agent will get if it takes that action at that state. This is an iterative process, as we need to improve the Q table for each iteration. We initialize all Q values to 0 initially. For the first few iterations, when the agent doesn't reach its goal, the Q values for those state action pairs would keep going negative. After a few iterations, the Q values will start becoming positive and would guide our agent Tom in finding Jerry. So, how does this iterative process of updating Q values happen? Using the below equation, we update the Q values for state action pairs in the table. Pretty straightforward and simple, right? I know. Let's look at the gameplay and then discuss about the updation of Q values in the Q table. Notice a few things as the simulation runs for 10,000 episodes. You would be able to notice a decrease in the exploration rate. Exploration rate value of 1 means that the agent takes a completely random action. Exploration value of 0 means that the agent takes a completely greedy action. For an initial few episodes, you would see the agent taking more random actions to find out information about the environment. Later, you would see the agent taking greedy actions to reach the goal. As the episodes progress, the total number of wins for initial few states will be less, and in the later episodes, you would see Tom winning for most of the episodes. Towards the end, you would find that Tom always takes the most optimum path to find Jerry. Notice that the Q values would initially go negative, and once the agent starts winning, the Q values would start becoming positive, guiding our agent for the best possible action to take. Notice the Q table counter on the right side. Every time Tom reaches a state, the same is updated in the Q table counter. If the Tom reaches a particular state multiple times, you would be able to see the lines turning greener for those state action pairs. At the end of the simulation, we will discuss the updation of Q values in detail. So our agent Tom has found Jerry for roughly 8,000 times out of 9,500. That's interesting. Let's see what we can infer from this. You can see that the Q values are now positive. Also notice that as the agent nears the goal, the Q values become greater and greater for corresponding state action pairs. Wait for a bit and I'll explain why this happens. Notice that the exploration rate has gone down to roughly 2%, meaning out of 100 actions, the agent would take 2 actions randomly and the rest 98 actions would be the ones that give our agent the maximum reward. In the Q table counter, you can see that some portions are green. The green portions are the actions that our agent has explored more times compared to the non-green ones for those states. This is because of the exploration-exploitation trade-off. The agent takes the actions that yield more rewards because it kind of wants to gain confidence for those state action pairs. So essentially, the reason for certain peaks is because the agent, once it knows a particular path to reach a goal, it slowly stops exploring the other paths. Let's see how the updation of Q values happen. Start state for the agent is fixed to 580 and the goal position is set to 598. For every cell, the state value is present in the center and the corresponding state action pairs are present in the 4 directions. You can notice that the agent has started taking random actions as the exploration rate is high. While the agent takes these random actions, the Q values for these state action pairs start becoming negative as they do not yield a positive reward. Let's consider the state 593, from which taking an action in the right direction would give Tom a reward of plus 10. Notice that the Q values for this state action pair has been updated to plus 1. Remember this equation? This is what is used to update the Q values for every state action pair. Learning rate alpha here is 0.1 and the discount rate gamma is set to 0.99. You can notice that the Q value for right action from state 593 would keep increasing until it reaches 10. This would be true for all the states adjacent to the terminal states, namely 597, 592, 593, 594 and 599. This is because taking an action towards the terminal state from these states gives a reward of plus 10. Let's understand the gist of this process of updating Q values for other states. Consider 2 states, state 1 and the next state. The agent takes an action from state 1 to reach the next state. If the maximum Q value for this next state is higher than the state action pair for state 1, then the Q value for this state action pair increases. Similarly, if the maximum Q value for the next state is lower than the state action pair for state 1, then the Q value for this state action pair decreases. Also notice that the agent does not visit all the states equally. It quickly discards those states that do not yield a good reward. In the next video, I would discuss a few more things, mainly the impact of learning rate and discount factor in Q learning. Before concluding this one, I would like to state one of the interesting life analogies here. In life too, we have to be diligent and smart to achieve our goals. You have noticed that our agent is hardworking enough to keep taking actions even if the actions do not yield any reward. Also, our agent is smart enough to discard those actions that do not yield any reward.